Hello, I'm Eduardo, and today I'll be your guide in this path towards decentralized proof of location. So, reality, like Einstein once said, is merely an illusion, but maybe a very, very persistent one. So, in the spirit of keeping our brains a bit busy wondering of this nature of reality, I would like you all to think for a brief moment in a couple of scenarios. For example, how would Joe Biden prove the authenticity of this wonderful review that he just left of this restaurant? Or for example, the Pope after buying that fancy jacket? Or for example, how a reporter certified the integrity of his pictures and videos taken after covering an important event, or for example, spotting an important person? Or a service provider to prove the supply or the delivery of goods at a very specific location? Or for example, how would I prove to someone else later that I was here in this room before all of you at this moment in time giving my presentation? Well, hoping to keep your brains a bit busy, today I'll introduce you to the proof of location paradigm. We will go through the evolution of proof of location systems from trusted and centralized architectures to eventually decentralized protocols, where I'll show you my attempt at design of a novel decentralized proof of location protocol and implementation of a proof of concept. But we will go to details of all the steps in the presentation. But going back to all those crazy scenarios, well, prove one's location, prove the existence of something in this reality. These are actually part of the set of today's problems that the typical GPS-based location systems, navigation platforms, mobility apps, well, they don't have straight answers for. And with this present surge of highly realistic generative AI tools that start to make us question and wonder what is real, what is fake, what we may need instead is this paradigm shift towards digital proofs of location. These proofs are nothing more than electronic certificates that attest one's position in both space and time. And typically, these location proof arrangements expect the existence of a prover that engages in any short-range communication protocol with nearby participants, the witnesses, with the goal of gathering a verifiable proof of location claim to then present to a verifier, therefore convincing it of the prover's existence within a geographical area and at a given moment. So having, with this proof of location paradigm in mind, location proof systems started with a trusted and centralized architecture with trusted entities that would interact with each other to provide verifiable space and time references, and progressing towards more distributed systems, for example, increasing the number of entities, until we finally reach the modern era of decentralized protocols. And here, the distribution of trust, resources, power, profit, fault tolerance, the end goal of taking advantage of all the devices around us, laptops, mobile phones, routers, sensors, is what has driven the development of these modern protocols, to culminating in the need for not only short-range communication, but also decentralized time synchronization. Well, to leave you with some thoughts attesting to my presentation here, all of you today, how could we all be here in this room now if our clocks were not marking a similar time? So yeah, these are the main ideas behind most proof of location protocols, which are generally considered secure if complete, meaning if they can provide both space and time references, spatiotemporally sound, or in other words, if it would be very hard for the prover to still get a valid proof of location if the prover was not physically there and at that point in time, and non-transferable, meaning if the certificates are valid only for one prover. So yeah, having identified this need for both space and time synchronization, now I'll show you the design of a novel decentralized proof of location protocol and the eventual implementation of a proof of concept to showcase how one can now start generating complete, verifiable, and spatiotemporally sound location proofs. So yeah, the design journey of the protocol started first by identifying a suitable network topology to meet the first requirement of space synchronization. And the perfect fit seemed to be the concept of dynamic and non-hierarchic mesh networks. This type of network topology allows for the peer-to-peer short-range communication between the devices in a decentralized way, meaning with no central or routing or coordinating device. Of course, the transmission of data starts in the physical layer with the physical arrangement and placement of the devices, their physical connections, the frequencies that they use, and the topology eventually gains form with layer 2 routing protocols that determine the path for data to travel. These protocols are also responsible for the processes of discovering nearby nodes and the ranking of their links. First, for optimizing communication paths, increasing the overall efficiency of the mesh network, and second, for the targeted establishment of zones within the mesh network. Zones are these strongly connected sets of neighbors that, in the case of this proof of location protocol, are set to establish this concept of space synchronization and so provide witnessing capabilities. So then all these concepts in practice, I implemented them in a lab environment, but by taking advantage of a set of existing technology. For example, I used OpenWRT as the operating system, which is a typical choice for this type of networking scenarios, QEMU as the emulator environment, and finally, the most important one, I used Batman ADV as the layer 2 routing protocol. My testbed contains a set of witnesses and a prover instance, all connected to a bridge interface that in this case is set to pull all the raw mesh traffic, simulating the eventual constraints of a physical medium. But at the end, the goal is to have wireless cards, Bluetooth interfaces. Then we jump to the layer 2, and here we can use the max sublayer, and on top of it, we enable the Batman ADV for the discovery of nearby nodes, peer-to-peer connections, and the eventual formation of this witnessing zone. Then on top of Batman, we can use the TCP/IP suite of protocols to enable the typical internet connections that now we all know how to work with. So the final network architecture looks like this figure on the right, which is now ready to see deployed any typical web service abstracted from this concept of a strongly connected peer-to-peer short-range mesh network. So yeah, with this first effort, we have achieved the first step of space synchronization. Well, again, to leave you with some thoughts, this, in our case of attesting to my presentation, represents the fact that we're all here in this room and we restrict our physical communications to this room only. We can talk to each other in a peer-to-peer way, but not with someone else outside or someone who's very far away. So yeah, then the second set of requirements was to achieve time synchronization. And this need has been identified in the most recent decentralized protocols and somehow solved with a clock synchronization mechanism. I've reasoned into it and found some similarities between this and the typical consensus problem in distributed systems. Or in simple terms, synchronizing clocks is nothing more than reaching agreement about the current time of the internal clocks of a set of machines. This agreement can then be extended to achieve consensus about the current state of the system. And so here we can use a consensus mechanism to make the witnesses to agree to pace the network events at the same rate and so achieve consensus and zone relative time consciousness. So using a consensus mechanism also has the added benefit of providing this strongly consistent serialization of transactions and total order of multidimensional events instead of this old way of simply counting time in one dimension. Also, assuming a trustless environment, this problem can be transposed to the problem of achieving permissionless consensus, and so fulfilling the need for ordering and synchronizing events in an environment where individual participants are not necessarily trusted. And then on top of that, we can use a Turing-complete system to allow for the witnesses to also agree to perform arbitrary computations. This enables something like smart contracts as dictated by the direct consensus between the entities of the protocol. And now, one may not just create a proof for one prover, but let's say, for example, for a group of provers, or enforce the existence of the prover at a very specific point in time, among all other programmable scenarios now. So these ideas then, in a practical way, I implemented them on top of the mesh network via the deployment of a blockchain framework. For this case, I chose Ethereum to play around and experimented with the multiple consensus protocols and also with multiple properties of this type of networks, for example, the block time, the interval between blocks. Everything was initialized in the Genesis file, and building upon the mesh network infrastructure, the Ethereum nodes were actually able to discover each other, establish peer-to-peer connections, and so start producing blocks and achieve that time synchronization. Ethereum was also chosen because of the smart contracts capabilities, which were written in Solidity and executed in the Ethereum virtual machine on each individual witness. So now that we achieved both space and time synchronization for the witnesses, the prover can come and take advantage of the synchrony to finally request a proof of location certificate. So this diagram on the right shows the prover process, and basically the prover, assuming that he can talk with the witnesses via the same short-range communication channel, the prover needs to prove as well that he is synchronized in time. So first, the prover needs to learn about the zone's clock or the zone's most recent time. Then the prover assembles, signs, and submits a transaction claiming that he learned about the zone's clock. Wait for the witnesses to validate the transaction, and finally, the prover can request the witnesses' signatures to assemble a proof of location certificate that now can be verified like any typical digital signature verification process and integrated with applications of all kinds. In my proof of concept, I ended up being able to implement both these flows, generation and verification processes, also taking advantage of smart contracts. But this can be integrated and implemented in any environment. So then I did some performance measurements to try to understand the behavior of these sub-protocols. And well, very, very generally, what I found out is that these are actually protocols suitable and adaptable to resource-constrained environments. For example, mobile phones, microprocessors, routers, the sensors around us. But there's still a missing piece of the puzzle. Here, I tried a final test to understand the relation between this property of the block time, the interval between two blocks, and the success rate in generating spatio-temporally sound certificates. And essentially, as you can see, a more permissive block time allows for a larger success rate, but it actually opens up the possibility for what I've identified as the so-called proxy attacks. That is, when an adversary can act as a proxy, and in the interval between two blocks, the adversary is fast enough to first synchronize with the zone, ask for the zone's clock, second, ask a remote prover for a transaction signature, and third, submit the transaction. Well, with this, I concluded that the block time actually plays a very crucial role in the soundness of the protocol and needs to be adjusted carefully to mitigate this kind of attacks when a remote prover is still able to generate a valid certificate without being nearby the witnesses. So, to recap, today I introduce you to the proof of location paradigm, identifying the entities, their interactions, some real-world applications. We went through the evolution of proof of location systems from trusted and centralized architectures to eventually decentralized protocols, where I showed you a novel decentralized proof of location protocol for both space and time synchronization and implementation and evaluation of a proof of concept, making use of already existing technology, mesh networks, and blockchain frameworks. Well, for the future, yes, still a lot of work to do. From identity management systems, incentive mechanisms for the creation and expansion of witnessing zones, taking full advantage of smart contracts and their full set of capabilities, researching or finding or creating new consensus protocols, maybe implementing privacy-preserving technologies on top of this proof of location protocol. And of course, the end goal is the physical deployment of the solution and the evaluation of the performance in real-world applications. Finally, allow us to start getting proofs of our existence and proofs of our location and contribute to the creation of complete, verifiable, and spatio-temporally sound location proofs. Thank you.
Aitäh Eduardole. Thank you.